flip-flops or flip-flops. But I didn't need else. They would. Well, this is a white flip-flops, so like. They're not quite flip-flops. Yes. They're great for health. Yes. What are you dressing it for? I'm to bed early.
Okay, so let's go ahead and begin. So, as you can tell from what's up on the board, we're going to start discussing sequential circuits. So, remember, up to this point, all the circuitry that we've been covering is referred to as combinational. Also, sometimes it's called combinatorial. So, combinatorial, same thing. Okay. So yeah, today is when you'll find out what that word latch means that we've been talking about. That one.
Oh my
If
goodness.
you get in the warning, you treat it like an error. So
Been waiting for this.
all right,
Is it really that scary?
not as scary as some things. You'll probably find it interesting. So anyway, do you remember when we were talking about combinational circuits, right? I think I brought this up the first time when we were modeling combinational circuits with either an if statement or a case statement. It's got to go in an always ohm block, and ohm is short for combinatorial. And I think I mentioned at that time that combinational, again, same thing. It doesn't have something. It has no what. Okay, memory is the one I mentioned in class, but as we're going to discover here, if you don't have memory, you don't need what's called a clock signal. We'll talk more about exactly what we mean by clock signal here in the digital case. Now, combinational circuitry, it doesn't have these two things. Sequential circuitry does have those two things. The sequential circuits does have memory, and therefore it has a clock signal. So that's the big difference between the two. And then also the definition of a combinational circuit is that with a combinational circuit, and this is my shorthand for combinational, our outputs only depend on the inputs. Right, like all the circuitry we've built and talked about up till today, to determine what the output was or outputs, if there was more than one, we just had to look at what the inputs were, right? And then you would just follow the inputs through, to see what kind of logic signals you would get until you reach the output. Well, sequential circuits, the output or outputs don't only depend on the inputs, but they also depend on the output. So, where this would be a high-level black box diagram of any combinational type circuit, like, real general type of high-level black box diagram, a high-level black box diagram of a sequential circuit would look something like this. I mean, you can have a number of inputs, but then you would have at least one output that feeds back to an input. Okay, see, when you make a connection between an output and an input, that's called feedback. Okay, so memory circuits, digital circuitry with memory, it has feedback. So the output, I apologize if this is too low, I was trying to squeeze it in here. But I mean, the definition just goes with this high-level black box diagram that outputs of sequential circuits depend on inputs and outputs. Okay. All right, so why is memory important? Well, one of the reasons why memory is important is because if you have a sequence of events, like let's just say you have a number of events. They can be anything. So, I'm talking in very general terms here. We're going to get more specific as we get to examples, the rest of the quarter. But, let's say you just have like event A, event B, event C, event D, event E. And there's a sequence of these events. Like maybe if you're in event A, well, from A, you go to B. And maybe if you're in event B, from B, you go to E. And then if you're in event E, you go to D, and so on. There's a certain sequence. Well, in order to have a sequence like this, in order to go to the next event in the sequence, you have to know where you are present, right? Like you have to have previous information to know where you're going next, okay? And that's where memory comes into play, right? Because to know where you're going to go next in a sequence, you got to know where you are first in that sequence. Okay. All right. So remember, our most recent major topic, signed binary numbers. Remember how I talked about there was two meanings to two's complement, right? There's two complement. Two's complement, the noun, which is just a listing of, what numbers you can represent depending on, how many bits you have in your two's complement. But then there was the verb take two's complement, which if you take the two's complement of any signed binary number, it's going to negate it. Okay. Well, it's the same sort of thing with the word latch. Okay. There's a meaning of the word latch as a noun, and there's a meaning of the word latch as a verb. Okay. As a noun, it's a circuit like this. It's a logic circuit like this. What kind of gates are these? Right. Now you could make a latch with NORs. Okay, so this is a NAND latch, but you can also have a NOR latch, which would look just like this diagram, except you'd have NOR gates instead of NAND gates. And the noticeable thing here, or the key feature of a latch, is how the outputs connect back to the inputs. Q and not Q, these are outputs. Okay, and S and R, those are inputs. Okay, so notice how the Q output of this top NAND gate, it connects to an input of this bottom NAND gate. Okay, and the output of this bottom NAND gate connects up to an input of this top NAND gate. This type of connection, it's called cross-coupled. Okay, so the way you make a latch is you either take two NAND gates and cross-couple them, or you can take two NOR gates and cross-couple them. Okay, so that's latch the noun, which is the actual logic circuit. Latch the verb just means to store or to hold. Okay, like you latch onto something. Here it's latching onto data, which are zeros and ones. So any questions up to this point? This is sort of like, general preliminary type of overview kind of information before we get to the nitty gritty, okay, which is analyzing a latch circuit like this and to see why, it gives us memory, okay? Okay, so you can see I got a couple of tables here. In this table, I've got S and R and Q on one side. And remember, we consider the left side of a truth table the input side. And then on the right side, I got this Q with the plus sign, and that's what we're going to consider what the output is. Then I got another truth table right next to it. We're going to start with this truth table, and then we're going to take this truth table and condense it down into this one. Okay, so that's why I see two side by side. Now, this diagram here of the cross-coupled NANDs, that's an actual latch circuit. Okay, so this is the actual latch. Okay, up here, see I have another diagram, and it's got the two NAND gates, and then it has this block with TD. TD stands for time delay. So this diagram is just an analysis circuit. Right? I mean, this you could actually like physically connect up or physically model, you know, in Verilog. You know, this you couldn't like physically connect because there's no way to like physically have like a time delay, like a block of time delay. Okay, but it's there just to help us do an analysis. Okay. Now, at the output side of this NAND gate, that's where our Q plus. Okay, and on this side of that block time delay is where Q is. Now Q stands for, and everywhere you see a Q in the truth tables in that diagram, the Q stands for, let's write it over here. Okay, the Q stands for present state. And what the value of the output Q is present, okay, the present state. Okay, Q plus, that's the next state of Q. Okay, so just Q is present state, Q plus stands for next state. That's what output Q is going to be. Right? Q is what it is now, Q plus is what the output is gonna be. Okay? Okay, so we're starting with this truth table, and we're gonna fill out this truth table by using this analysis circuit here. So first of all, since I have 3 inputs, I'm treating this present state Q as an input. Okay, so that's why you see 3 on the input side of the truth table. So since I have 3 inputs, how many combinations do I have? 8. 8. So let's fill that out. So I got 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1. Okay. So again, 2, 4, 6, 8. If I make a mistake, let me know. Okay, yes, it's in binary order. Okay. All right, so now we're going to fill out what the next state of Q is by analyzing this circuit. Okay. All right, so now this is probably what the 3rd time, you know, I've said this that, you know, you have a truth table, but really what's important is understanding a truth table. Right? Remember, we've done that a couple of times. And just like we've done in the past, you can kind of split the truth table in half. Now, I didn't fill out the output side because I was hoping you could tell me. What's the output side of this NAND gate truth table going to look like? When's the only time you get a 0 out of a NAND gate? Yeah, you only get a 0 out of a NAND gate when all the inputs are 1, right? Because it's like an AND with an inverter on the output, right? You only get a 1 out of an AND gate when all the inputs are 1. So you only get a 0 out of an AND gate when all the inputs are 1. So you got a 0 here, but then the rest are 1s. Okay. Well, now if you split this truth table in half and you just look at the top 2 rows, do you see what the top 2 rows are telling us?
The answer is one of the inputs is 0, it's always going to be output 1.
Exactly, right? The 2 rows up here, see if one input is a 0, like if your A input is a 0, the output's going to be 1 regardless what the other input is. Okay, now, if you look at the bottom half of the truth table, what does the bottom half of the truth table tell us?
A is 1, the output depends on B.
And how does it depend on B? Right, exactly that. The other 2 rows of the truth table tell us that if one input to a NAND gate is a 1, the output's going to be the opposite of what the other input is. Okay, so you see, by understanding the truth table, it can help you do the analysis. It can make the analysis easier. All right, so let's go ahead and start. We're going to just start with this first row. The first row, S is 0, R is 0, and present state of Q is. And I want to get next state of Q, which is the output of this NAND gate here. Well, look, since this input of the NAND gate is a 0, do I have to even bother to find what this other input is? No, because I understand the truth table, and I know that if one input to a NAND gate is a 0, I'm going to get a 1 out. right? This is gonna be a one regardless what this other input is. Okay, so you see how it saves you time, right? Because once I see that zero there, I can say the output is one. I don't even have to bother analyzing the rest of the circuit. Does that make sense? All right, so you see that's gonna be a one. All right, go to the next row. The only thing that's different is this becomes a one. Right, S and R are still zero. This becomes a one. Well, is that going to change this answer? Nope, because S is still zero. So the output of that AND gate is still going to be a one. All right, let's see the next row. The next row, S is still zero. This is one. In present state of Q is zero. Is that going to change the answer? No, it's still a one because S is still a zero. Right? So this is still going to be a one. Now the next one, S is still zero, R is one, Q is. Is that going to change our answer for next day? Q? Still going to be, right? As long as S is zero, Q plus is going to be a one, right? Everybody agree? So you see how my first four rows are one? Right, so any questions up to this point? What's your Q is right on the right side of this timing delay block. So Q plus is on this side and Q is not. See, Q is the output now, Q plus is the output sometime later, and we're putting this time block in between just to separate the time. You know, they're both the output Q, but one, they're at different times. One is now, one is later. Okay. All right, let's go to this row here. Now, S becomes a one now. Okay, so S is going to be a one now. And then what we got? We got R zero and R is zero and Q is zero. All right, so since this input to this, then, right, that has the output I'm looking for. Since it's a one, now I have to find what the other input is, right? Because once I find what this input is, the output's going to be opposite. Right? Again, that goes from understanding the truth table, right? One part is understanding the top half, the other part is understanding the bottom half. Okay, so you have to find what this input is. Well, this Q here, right, the present state of Q, it's directly connected to this input of this NAND gate. So whatever present state of Q is, that's what this input is. Right, so you see, since Q is zero, this input of this NAND gate zero. So I got two zeros to the NAND gate, that's going to give me a one out. And a one out of here, that's connected right to the input of this. So what's my next state of Q going to be? Zero, right? It's going to be the opposite of what this is. Right? Two ones give us a zero. So you see, this is going to be a zero. All right, let's see the next row. S is still one, R is still zero, but now this becomes. All right, well, that's a one, it's gonna make this a one. And my output's gonna be still a one. Still a one, right? In fact, actually, since this is a zero, right, we don't even need to find that. We could have just said, oh, based on that being a zero. Okay, but either way, it just comes out the same, right? Because this is going to be zero here. Right? Everybody agree? Okay. All right, the next row, this is zero. And R is one. Right? So Q is zero, S is still one, R is one, Q is zero. All right, so again, this zero is connected right here. Okay, what's our output going to be? Zero. It's going to be zero. Make this a zero, which makes our next state of Q what? A what? A one. Yeah. Okay, and then the last row, everything's a one, right? All the inputs are a one. So this is a one, make this a one, which makes this zero. Zero. So I have the same, another one, right? Does that match what I had earlier? Actually, did we make a mistake here?
Is the 110 correct?
Yeah, that's the one. Let's go back to this one. I think we made a mistake here. Let's go back to this. See, you gotta keep an eye on me. Let's see, S is 1, R is 1, this is 0. Right? Let's erase these. Okay, so this 0 connects right here, which is gonna make the output what? A 1. Makes this a 0. So you see, we made a mistake. Right? This should be a 0. Okay. Everybody see that? Happens to the best of us. Okay, so are you confident that you could do a table like this, right? Because in the past, I'm not going to do it this time, but in the past, what I've done for the activity, I have a different activity today. I'm giving you more practice with timing diagrams. Because that's one of the topics on the midterm. Although, like I've said, sequential circuits are not on the midterm. However, you could have a timing diagram that has something to do with the combination circuit like we've been doing. So I figured, even though these timing diagrams have to do with sequential circuits, at least it's more practice with timing diagrams. But what I used to do in the past is I would have the activity where I would give the students a NOR latch, right? So this same circuit with NORs and ask you to do the same thing. You may want to do that just as some practice. But anyways. All right, the next thing we're going to do is we're going to take this truth table and just condense it into a smaller truth table. Instead of having SR, our inputs to the latch along with present state Q shown, we're just going to do SR just with next state of Q shown. And the way we're going to do that is we're going to take this truth table and just look at it 2 rows at a time. I'm taking this, I'm just going to every 2 rows and kind of dividing it up. Let's see, these 2 rows, these 2 rows, these 2 rows, these 2 rows. Now, we're going to start with these 2 rows. We'll come back to the first 2 rows in a little bit. Okay, but let's just look at these 2 rows. See, these 2 rows, S and R are both, or S is 0 for both rows, and R is 1 for both rows. Right? See that? These 2 rows here, 0 and 1 for S and R. And for both rows, the next state of Q is 1. Okay, so you see, if input S is 0 and input R is 1, whatever the present state of Q is, the next state is going to be 1 regardless. Okay, and this is given a name. Okay, when the next state of Q is going to become 1 regardless of what the present state of Q is, this is called the set condition. And we say that the latch is set. Now, this is really important, okay, because this is a common misconception. The word set just refers to the next state of Q being 1. It doesn't refer to what the input values are. I mean, in this particular case, for a NAND latch, you need S equal to 0 and R equal to 1 to get the set condition. But if you had a NOR latch, you would get the set condition for a different set of inputs, a different set of values of inputs. Okay, so set just simply means the next state of Q becomes 1. Okay, and for this latch, it happens when S is 0 and R is 1. Okay. All right, now let's look at these 2 rows. These 2 rows, S is 1, R is 0, and regardless what the present state of Q is, the next state of Q is going to be 0. That's called reset. And again, reset refers to the value of next state of Q. All right, now this is why this circuit exists. Okay, these bottom 2 rows. Because these bottom 2 rows, if both S and R are both 1, look, next state of Q just equals present state of Q, right? Because if the present state of Q is 0, the next state of Q is going to be 0. If the present state of Q is 1, the next state of Q is going to be 1. What do you think we call it? Because if the output value is the same a time later as what it was previously, and say that 1 or 0 is part of information, part of data, right? We know that zeros and ones represent data like binary numbers. And like we said, like zeros and ones can represent anything, right? So if you think of these outputs of the latch being data, we have data from a previous time, right? What's that?
A bit.
Well, yeah, these are all bits. And whether the bit's a 0, yeah, whether the bit's a 0, bit is a 1, we're retaining the bit values from a previous time, right? Because the next data Q, right, and the value of Q, those are just the bit values, is the same as the previous value of it. So you see, this is memory. This is called the hold state. When the next data Q equals the present state of Q, that's hold, that's latch, that's memory, that's store, whatever you want to call it. Right? If I can retain bit values from a previous time, then I've remembered, or the circuit has remembered, right? See, this is why this circuit exists. Now, I purposely left the top 2 rows for last because there's something peculiar with what these top 2 rows tell us. When S and R are both 0, you can see that next data Q is 1 in either case. Now, this is where just looking at the analysis circuit doesn't tell us the whole story. If we look at the actual circuit, we see that there's something peculiar, okay? Because if we look at the actual circuit here, and I have S0 and R0, can I find what Q and not Q are without finding what these other inputs are? Like, do I even have to care about this cross-coupled type of connection? Because what? Yeah, because as we said earlier, right, when we were talking about the top 2 rows here, if one input to a NAND gate is a 0, the output's a 1, regardless what the other input is. So look, if you have S equal to 0 and R equal to 0, both outputs are 1. See a problem with that? This is the Q output, this is the not Q output. They're both 1. Right, see, this doesn't make sense based on our Boolean algebra definitions, right? Because in Boolean algebra, we use the bar, right, meaning not that variable. It means opposite of. And you see this circuit, when both inputs are 0, it gives us both outputs equal to 1, which goes against our definition of those outputs, the Boolean definition. So this top state, when both Q's, next data Q is 1, we call it the forbidden state. So I guess it is a kind of scary class, right? It's also called ambiguous. Sometimes you'll see it referred to ambiguous, and then other times forbidden. And the reason, again, that it's forbidden or ambiguous is because it goes against our definition of what not a variable is. So, this state is to be avoided at all costs. Well, it's not like something's going to blow up or Freddy Krueger's going to come into your dream.
No, it's a lot of things to avoid it.
But it's typically something you don't want. Yeah. And the way you avoid it is just make sure the inputs are never those values that would give you that state. Okay. Now, you're going to see coming up, we're going to get to something called a flip-flop. And the flip-flop was an improvement over the latch. Okay, in fact, you're going to see that a flip-flop is a latch plus some additional circuitry that gives it a feature that is advantageous over a latch. So, the latch was sort of like the most primitive of memory circuitry, if you will. And then there was improvements over that, what the flip-flop is. Okay. But yeah, the latch itself, it has this state that, We wish it wasn't there, but you see, the reason why this latch circuit exists is because of this. It gives us this property of memory. The forbidden state, that's kind of just like baggage that comes along with it. Okay, but like I said, later on, when they developed the flip-flop, in a way, took care of this ambiguous, although not totally, as we'll get to. Okay. All right, so I think I got to move the camera now. So, any questions before I move the camera? Because we're ready to talk about a flip-flop. I think the most key thing to understand so far today is this right here, the understanding that if you retain previous bit values, that's storage of data, right? You're remembering data from a previous time. Okay. Let's move the camera. Talk about it. Oops. Let's see where we get it. Okay, let's get it. All right. So a flip-flop is a edge sensitive latch. What's that?
Thought it was footwear.
Well, it's that. And I'm going to talk about what's meant by edge sensitive, but that's the definition of a flip-flop. It's an edge sensitive latch. Now, here's where I'm going to refer you to a couple of different references. And the primary reason I'm doing this is, one, to save time, because it would probably take me a good 20 minutes at least. And also just because the video that I have that explains, explains the inner details of a flip-flop, how the edge sensitivity is achieved, is done really well in my opinion. So the two references I'm talking about is one reference that's on your table. I put a handout, this handout here, one on each table. Again, you can take a picture of it. I think this is also on Canvas. I mean, there's a couple of different things here, but what's important or what's relevant at this point is up in the upper left-hand corner. See this logic circuit? Can you see that there's part of it that should look familiar?
With a latch.
Yeah, see the latch, there is the latch there. See the NAND gate latch is there. But then we have additional gates. See, there's two additional NAND gates and there's also a NOT gate. Well, that additional circuitry, those additional two NAND gates and that additional NOT gate, that's what gives the edge sensitivity. Okay, and I'm going to talk, I'm coming up here, I'm going to talk about what edge sensitivity is. But if you take a latch, an NAND latch, and add those additional gates, you'll get what's called edge sensitivity. And like I said, there's a video I put on Canvas. It's about a 15-minute video, maybe 20 minutes. And in my opinion, it's a really good explanation how that additional circuitry gives you this edge sensitivity. They use like animation and something I can't do with the board. So that's why I think the video is better. But I'm going to give you the end results. Okay, so there are different types of flip-flops. There's what are called T flip-flops, there's JK flip-flops. But the most common and the one that we use in this class, and the only one you're responsible for, is called the D flip-flop. Okay. And there's two types of D flip-flops. And I've drawn the symbol for each type. Again, the Qs are the outputs. All right, so Q and not Q are outputs. That's pretty standard with flip-flops. No matter what kind of flip-flop you have, the outputs, I don't think I've ever seen outputs of flip-flops labeled anything other than Q and not. But what's different with the different flip-flops is what the inputs are labeled. For a D flip-flop, you have a D input and you have a clock input. CLK stands for clock. And you see how there's like this little triangle or this little greater than right at the clock input. That identifies that it's edge sensitive. Now, do you see the only difference between the two symbols?
There's a NOT.
Yeah, see, the only difference between the two is that there's a little bubble right at the clock input on this symbol. And that's what distinguishes between the two different types. This type that doesn't have the little bubble, it's called rising edge trigger. Okay, RET, rising edge trigger. And when it has the little bubble, it's FET, which doesn't stand for field effect transistor here if you've had electronics. Here it stands for falling edge trigger. Now, unfortunately, there's other names for rising edge and falling edge. You might have heard them if you've taken it like an EE lab, especially. Have you heard of rising edge? Or, well, I just said rising. Have you heard of leading edge? Leading edge and rising edge are the same thing. Have you heard of positive edge? Yeah. So rising edge, positive edge, and the other one I said, rising edge, rising edge, positive edge, and leading edge. And then falling edge, there's also trailing edge, and there's also negative edge. Okay, they all mean the same thing. Rising edge refers to a transition from 0 to 1. Okay, so you see that's a rising edge. And a falling edge refers to a 1 to 0 transition. Okay, so that 0 to 1 transition, the time that happens, that's what's referred to as rising edge or leading edge or positive edge. This would be falling edge, trailing edge, or negative edge. Okay. Okay, so that's the two different types. Now, we got the two different truth tables, and let me go ahead and fill them out, and then I will explain that. So here, let's see, this is rising. This one out. Like I said, I'm filling this out. I'll explain it once I have it filled out. Okay, so notice the only thing different in the truth tables is in the clock column is the direction of the arrow. Right here for the rising edge, the arrow is going up. Here for the falling edge, the arrow is going down. Other than that, the truth tables are the same. See, if you have D0 and the present state of Q0, your next state of Q is going to be 0, right? And that's the same for both truth tables. If D is 0 and the present state of Q is 1, well, next state of Q is going to be 0. And if D is 1 and the present state of Q is 0, well, next state of Q is going to be 1. And if D and the present state of Q are 1, well, next state of Q is also going to be 1. And so the truth tables are the same, except again for the direction of the arrow. Well, the direction of the arrow refers to the edge. See, since this is rising edge, that's why you see the arrow going up. This rising edge means a 0 to 1 transition. And the reason you see the arrow going down in this truth table is because this is the falling edge D flip-flop. And falling edge refers to the 1 to 0 transition of the clock. Okay. Now, notice that if we split these truth tables in half, notice that if D is 0, no matter what the present state of Q is, the next state of Q is going to be 0, right? And if D is 1, no matter what the current state of Q is, the next state is going to be 1. And that's the same in both truth tables, okay? So the way that you can summarize in words how these flip-flops work is that next state of Q will equal input D at the time of the appropriate clock transition. And what do I mean by appropriate? Well, the appropriate clock transition for a rising edge is the 0 to 1 transition. And the appropriate transition for the following edge is the 1 to 0 transition. Okay, so the next data Q is only going to equal the input D at the time of the appropriate clock transition. For all other time of the clock transition, the next data Q is just going to equal the present state of Q. Okay, so for all other times, the next data Q is just going to equal the present state of Q. See, the only possible time that the Q output can change for a D flip-flop is at the time of the appropriate clock transition. So when is data being stored for a flip-flop? Is it being stored at the time of the appropriate clock transition, or is it being stored for all other time other than the appropriate clock transition?
All of it.
All other time, because for all other time, the next data Q equals the present state of Q. That means you've retained previous information, right? You've retained previous zeros and ones. Does that make sense? Now, the advantages of a flip-flop over latch, because remember, both of these store data, right? The latch will store data, the flip-flop will store data. Do you see an ambiguous state in the truth table for a flip-flop?
Nope.
There is one for the latch though, right? So you see, that's one advantage. One advantage is a flip-flop doesn't have a forbidden state in the truth table. I'll put TT for truth table. Now, as I'm going to show in a timing diagram, in just a little while, you can still have an ambiguous condition with a flip-flop. Okay, we'll get to that, but it doesn't have it in its truth table. Okay. The other advantage that flip-flops have over latches is that they're less susceptible. Susceptible is a hard word. Let's see, S-U-C. Who's good at spelling? It's S-U-S-C-E-P.
Bro, T-I-B.
Say it again.
T-I-B-O.
Is that right?
No. Right, yeah.
Thank you.
Oh.
Okay, so flip-flops are less susceptible to noise than latches. Now, unless you've had some experience in a lab, especially like an EE lab, I don't know how much sense this will make, but the reason for this is because noise is typically like voltage spikes in a circuit. Well, how many people have looked at a signal on an oscilloscope? Just about it. Okay. And you know, when you look at a trace on an oscilloscope, it's usually like a little fuzzy. Well, that little fuzziness, that's noise, right? That's variation in the voltage along the way, right? So it looks a kind of fuzzy. So, you know, noise are voltage spikes. Well, latches, the output values depend on levels of voltage. And as I've said before, you know, we think of zeros as being an exact amount of voltage and a one being another exact amount of voltage. But in reality, if you have a voltage that's below a certain amount, we call it a zero, and it's above a certain amount, we call it a one. Well, voltage levels are much more susceptible to noise because noise is like voltage spikes. So, you know, if you had something that was a zero and you got a spike going in the positive direction that was enough to flip it to a one, well, that's a problem, or potentially it's a problem. And same way, if you had a one and you got a spike going in the negative direction, it could make it a zero. Okay. Well, the same is true for flip-flop, but the difference is the noise would have to happen right at the time of an appropriate clock transition. So the odds are less that noise would cause a problem with a flip-flop compared to a latch. And it's because of the edge sensitivity. That's what makes it less immune to noise. It doesn't mean that it's 100% immune, because you could still get some noise right at that time of that clock transition. But again, it's less likely than with the latch, because the latch is a level sensitive. Okay, so we're getting close to the top of the hour. Why don't we take about a 5-minute break? Because I think it's going to take me another half hour, because once we get to these inputs and what synchronous and asynchronous is, I think you'll have questions, because usually these do bring up questions. So why don't we take a 5-minute break, and then I'll pick up with this when you come back. So right at about the top of the hour, I'll start up again.
Well, I don't think clubs have certain sets built in.
Probably not all additional.
No, all the clubs can have, like, well, no, it's not the clubs here, just have like. Very big, like, you know, we club that they get, they'll always do have areas on set.
Oh, yeah. Yeah.
Well, basically, yeah, each of the clubs. And today. Well, I see all squads, the J. It's just like some back.
Okay,
Yeah, we can say cover like the J, but yeah, just be solid. But you might want, once you know one of the good clubs, you have.
Well, I got here.
Okay, so yeah.
Yes. Yes, so.
Everybody's saying like common. Like.
But these are.
It just refers to the transition. So the reason why for the rising edge trigger, I see an upward arrow on the G table, because rising edge refers to a 0 to 1 transition. So you know that 0 to 1.
Yeah.
And then just refers to the following it like.
Okay, that's just what I was looking at.
That's kind of what I.
That's just the. Here.
Well, the reason I drew both of these is just, I mean, this is what they're referring to. And
Yeah.
then, yeah, in the timing diagram, you know, in order to fill it out, one of the things you need to know is what rising edge or falling edge, because see, remember, it's at the time of that appropriate edge that the next data cue would equal the input D. Right, so, you know, if you have a rising edge and you got a timing diagram, you got to look at all the 0 to 1 transitions to see what D equals, because that's what your, you know, your Q values. Yeah, well, that's why the activity is timing diagrams. It's,
To help understand.
yeah, I think for most people, it takes a little while to get it all down.
Okay, yeah, it's. Oh, it's a lot of.
Yeah, yeah.
Yeah. First year. First year. I have to go with that.
That would start on your first.
Yeah.
Doesn't matter.
Yeah. And like. Well, like, I see.
They're like right before.
Okay, so I think it's about. Everyone's back there. Okay. Let's go ahead and start up again. And let's see, do I have to turn the camera yet? No. Remind me to turn the camera though when I get over there. I'm likely to forget it. I think I'm still in view. I am muted. Yeah, okay. All right, so now it gets a little bit more complicated. Because often on flip-flops, like a D flip-flop, you'll have additional inputs. These are your basic inputs. You're always gonna have a D input, you're always gonna have a clock input. Okay, with the D flips. But additionally, sometimes, and in fact, for lab 5, lab 5 is not gonna be due until the week after the week of the midterm, right? Because like I said, lab 4 is due the Friday after the midterm next week. So, you know, that time here for all this to sink in, but just so you know, lab 5, you'll have a D flip flop that also has these inputs that I'm going to talk about now. And one of the additional inputs is often called enable. Now it goes by other names too. In fact, I put them over here. Oh yeah, right here. Enable is also sometimes called load, and it's also called sometimes called enter. Okay, so load, enter, enable mean all the same thing in this case. And when the enable is activated, and I'm going to explain what's meant by activated coming up shortly. When enable is activated, well then next data Q will equal the D input at the appropriate clock transition. So it's like the enable is like an added condition in order for this to happen. Like if the enable is not activated, well, then your outputs are just going to stay the same all the time. Like there's no possibility that that at a clock transition that the next data Q would equal D. Okay, so that's what enable refers to. Reset, and when it's activated, again, I'm going to explain what's meant by activated. But when reset is activated, the next data Q is just going to equal 0. Okay. So no matter what the other inputs are, in fact, usually reset has the highest priority. Okay, so reset, highest priority. So when it's activated, it takes over. And it's just going to make your next data Q equal 0, no matter what. Okay, set is just the opposite of reset. Okay, when it's activated, Q becomes, or next data Q becomes 1. Okay, and it's usually the second highest priority. Second highest priority. And what I mean by priority here is that if you were to try to reset and set at the same time, reset would happen. And set's only going to happen if reset's not happening. And then if you're not resetting and you're not setting, that's when you would enable. Okay, so it's sort of like highest priority, second highest, and then this is like third highest or lowest. Okay. All right, so what's meant by activated? Well, there's 2 ways that you can activate an input. One is with a 0 and one is with a 1. If these are activated with a 0, they're called active low. All right, so let's say you have an active low reset. That means if you put a 0 on that reset input, that's going to make the next data Q equal 0. Okay, so the active value is what makes that input happen, right? If you have an active low set, well, you would have to put a 0 on that input to make the next state of Q1. You have a question?
Yeah, so we're like, is active low like R9 in that case?
Oh, are you?
I'm looking at it. Without
Yeah, I mean,
active low.
you are right. And when we get there, I'll mention it again. But yeah, you're thinking the right way. Yeah. Okay. All right. So what do you think active high means? If this is what active low means, active high means what?
I need the 1.
Yeah, it just needs the 1. Right. So active high a 1 on the input makes it happen. All right, so all of these inputs can either be active low or active high. You can have active low enable, active high enable. You can have active low reset, active high reset. You can have active high set, active low set. They can all those inputs can be either of those. You know, the way you usually find out is that you're just told in some fashion, like on the activity, you're just told, you know, for each timing diagram what they are. Now, sometimes they're shown in the actual symbol. If you have, say, an active high reset, you might see something like this. You might just see a line and then you'll see like RST for reset. Oh, also reset goes by clear. Okay, clear and reset are the same thing. So sometimes instead of seeing, you know, RST, you'll see CLR, which stands for clear, which again is the same thing as reset. If it's active low, like say you have an active low set, there'll be a little bubble. Right, so that little bubble would tell us it's active low instead of active high. All right, so you know, sometimes it's shown in the symbol, sometimes it isn't, sometimes it's just, you know, on a piece of paper that comes with like the manufacturing information for that, you know, flip-flop. And again, the activity I tell you in words. Okay, all right, but that's what enable, reset, and set in active low and active high is all about. So any questions up to this point? Because there's another 2 terms that's coming up, and these 2 are the ones that usually give, you know, if a person has some difficulty, usually it's with these 2.
What do you mean by makes it happen?
Well, reset means this, right? Reset means that the next data queue is going to go to 0. So if it's an active low reset, you got to put a 0 on the reset input to make this happen.
Oh,
Yeah, to make what the input means happen.
and is that just for a reset?
No, that's for all of these. That, yeah, whatever they are, like each one of these, right? These are 3 different inputs, and each one of these can either be active low or active high. And whatever makes them active, whatever it is, whether it's a 0, 1, well, once it's active, then you know, it will
So
happen.
each one has a 0 or a 1.
Right, yeah, right, because each of these is an input. Like here, you know, I wrote a reset, so you know, you could either have a 0, 1, just like a D input, because remember, this it's all digital signals here. Anytime we talk about an input or output for anything we're talking about, there's only 2 possibilities. Yeah. And you know, like enable would be another input. You know, like enable is often shown just, you know, EN. But again, there's other names for enable. There's load, there's enter is the other one, I think. So yeah, I know that's one of the things about, well, I guess it's just about every profession, right? There's often like multiple terms that mean the same thing. And that's part of the learning curve. Half of it is just getting the terminology right when you learn a new profession like you're learning. So yeah, but believe me, after some time, it's going to become like the back of your hand if you use it so much. Okay, so let's move on now and talk about synchronous and asynchronous, because each one of these inputs can also either be synchronous or asynchronous. And quite simply, the difference between the 2 is that synchronous depends on the clock. Asynchronous does not depend on the clock. Okay, so each one of these inputs, enable, reset, set, they can either be synchronous or they can be asynchronous. Okay, if they're synchronous, they depend on the clock. Asynchronous, they don't. And I think the best way to show the difference is in a timing diagram. Okay, but I mean, this is the different definition, right? One depends on the clock, one doesn't. All right, so let's take a look at this timing diagram I have here. So this is a timing diagram where, you know, these are our inputs here. Clock's an input 2, right? So these are our inputs. And then we're just looking at one output Q. You know, a lot of times you'll see this in timing diagrams for D flip-flops is they don't show Q and not Q, they just show one of them. And that's because you don't have an ambiguous situation. So you always know that not Q is the opposite of Q. Now, when you do a latch timing diagram, a lot of times they'll have both because you could have a situation if you hit the forbidden state where, you know, not Q and Q are the same, right? Like we talked about earlier. Okay. All right. As was mentioned earlier, the bar over R and the bar over S here, they don't mean not R and not S. Like it doesn't mean to flip these. Okay. In a timing diagram, you know, here's another thing where, you know, it's the same symbology, but it means something different in a different context, right? Because if it's part of a Boolean expression, you know, the bar does mean opposite of it. But here, the bar means active low. Okay, so this is active low reset, active low set. If it was active high, you wouldn't see the bar. Okay. All right, so we got our three inputs, we got our clock signal. Now, I don't think I mentioned this earlier, but the reason or what's meant by a clock signal in digital circuitry is a square wave that's periodic. Okay, so I tried to make this as periodic as I could. I actually think I did a pretty good job doing it from, thank you. Compliments are always appreciated. Now, even though these inputs to the flip-flops are labeled clock, that doesn't mean that the signal, the square wave that you attach to those clock inputs have to be periodic. I mean, often they are, but you could have a square wave signal attached to your clock input that's aperiodic. Like it could be low, then go high for a short amount of time, then go low for a real long amount of time, then go high for a different amount of time. You know, what signal you connect to the clock input doesn't have to be periodic, but that's where the name comes from, because a lot of times in a lot of different practical circuits, you do want a clock that's periodic. Okay. All right. So anyway, let's go ahead and find the Q for this D flip-flop based on this timing diagram. So like any timing diagram, you start at t equal to 0, right? And time progresses as you go left to right. Now, at t equal to 0, that Q output, it's got to be either a 0 or a 1, right? Because it's a digital signal, right? Binary signal, there's only two possible values. But unless we're doing an asynchronous reset or an asynchronous set, or unless we have an appropriate edge of the clock occurring right at t equal to 0, we're not going to know what that Q value is initially, right? It could either be a 0 or 1. Okay. So if you have a case like that where you can't distinguish whether the output is a 0 or 1, you can do a couple of different things. I mean, you could just put a question mark. Usually what I do, and usually what you'll see in most timing diagrams when that situation arises, and in fact, I think this is what the Vivado timing diagram will show when it, you know, it doesn't know whether a value of an output is, and maybe you've seen it already, because I think it puts an X in red. Okay, so that's what I'm going to do here. All right, see, I don't know what the Q output is. I know it's either a 0 or a 1, but I don't know which, because at this time, I'm not resetting, I'm not setting, and I don't have a clock transition. Okay. Over here, I'm providing the information as far as our inputs, like what kind of inputs we have. You know, I said earlier, we got an active low reset and it's synchronous. Okay, so it depends on the clock. And then we got an active low set and it's asynchronous, which means it doesn't depend on the clock. Instead of drawing enable with just a line for a 1, I'm just saying that enable has already been set to 1. Okay. And then also it's a rising edge trigger flip-flop. So once you see rising edge trigger, the only transitions that matter to us are the 0 to 1 transitions. Okay, if it was falling edge, then the 1 to 0 transitions would be the only ones that matter. Okay. All right. So we don't know what Q is to start with, but let's see what changes first here now. Hopefully I made it so, well, actually, let me just change this a little bit just to make it more clear. I want this to change before. Okay, so the first thing that changes as we go left to right is see right here that the reset signal goes from high to low. Okay, everything else stays the same. Okay, but that active low reset goes low. Now, the active low reset is synchronous, and synchronous depends on the clock. So what this means is that even though the reset went to the active value, right, the active low to 0, it won't actually happen until it's active low at the time of the appropriate transition of the clock. So even though the active low reset went to a 0 at this time, the Q output actually won't go to 0 until this clock transition occurs. See, because this clock transition happens at a time also when the active low reset is 0. So Q is going to stay in X, right? It's going to stay that we don't know what it is until the time of this 0 to 1 transition of the clock when the active low reset is 0, and that will make Q equal to 0. Okay, so this is a 0 right here. So any questions on that? Can anyone tell me the difference if instead of it being an synchronous reset, if it was an asynchronous reset, how would it change what I just wrote?
You would have it set to 0 a bit earlier.
Right.
Because the R dropped it to 0.
Yeah, exactly. See, if the reset was asynchronous does not depend on the clock. So if you have an asynchronous reset, the minute it goes low, so right at this time when it went to a 1 to a 0, that's when the reset would happen. So we wouldn't know what the Q output was until this time if it was asynchronous. Because it was synchronous, it not only had to be the active value of a 0, it had to be that active value during the time of the appropriate transition of the clock, which is rising edge in this case. Yeah, so you see if it's asynchronous, the reset wouldn't have happened earlier. It wouldn't have, wouldn't happen that amount of time earlier if it was asynchronous. And so you see, that's the difference between asynchronous and synchronous, right? Synchronous, it's not enough for that input to be its active value. It has to be that active value during the time of an appropriate transition of the clock. In this case, rising edge. If you understand that, you understand synchronous and asynchronous. Okay? All right, you're gonna get a lot of practice with these activities coming up. So, all right, so let's see. Let's see what else happens here. Well, at this time here, now we're not resetting anymore, right? Because now the reset's not active anymore. So this is just going to stay 0. So I erase this is still. Okay, so if you're not resetting and you're not setting, then the Q output is going to depend on what the D value is at the time of the appropriate transition of the clock. So this output's just going to stay 0 until we get to this first positive edge, or second positive edge, excuse me. See, right here at the time of this positive edge, D equals 1. So at that time, the next data Q is going to equal D. So it's going to go from a 0 to a 1. Right? Then you look at the next rising edge, because at the time of this rising edge, we're not resetting, we're not setting. Okay, so at the time of this rising edge, since D is 0, it's going to go to a 0. All right, and then let's see, then what changes next? Oh, did I do this on purpose? I think I did this on purpose. Yeah, I did this on purpose, because ours, yeah, see, look here, the next rising edge of the clock. You see how it's happening at the same time? Well, I tried to make it the same time. It's basically the same time. So just imagine they're perfectly lined up, because that's what I intended to do. Okay, so see here at the time of this rising edge of the clock, the synchronous active low reset is also going low to its active value. Do you see a problem with this?
There could like a small variation. Set it for that.
Yeah, exactly. This is ambiguous, right? Because if you have a synchronous input changing at the same time as the appropriate transition of the clock, you don't know what value it's going to take. You could flip a coin. So the reason I did this, and I did this on purpose, because even though a flip-flop doesn't have an ambiguous state in its truth table like a latch does, you can still have an ambiguous situation. See, this would be ambiguous, right? We wouldn't know what that output is, because we wouldn't know whether it was resetting or taking the value of D. And like I said, flip a coin, 50% of the time it would probably reset. The other 50% of the time it probably would take the value of D. Just one more thing, and I'll get. So as a designer, this is something you would want to avoid. You never want a synchronous input changing at the same time as the appropriate clock transition.
Didn't you mention the reset tends to take priority on? So when it like this.
Well, what I meant by that is reset takes priority over set or enable if they're happening at the same time.
Okay.
This is a clock transition. Yeah. Yeah. No, it's a good question, but yeah, it's just priority over these other inputs. Like there's no such thing as like priority over a clock. The clock is sort of like just keeping everyone, in the same beat, so to speak. It's kind of like a drum beat. Okay, and then I think the only other thing here is, when the set goes low, because it's asynchronous. So let's see this. So let's say, let's just pretend that's not there. Okay, because again, the only reason I did that was to make a point. Okay, I don't think you'll see any of those on the activities, but if you do, actually you might. If you do see one of these ambiguous situations on the activity, the person that made the solution to the activity, they took the value before the transition. So like in this case, since it's happening at the same time, they would take the value of R before, which means it's not reset. Okay, but that's sort of like an academic solution, if you will. In the real world, and also when you take CP 233 or even this class, when you do the final projects, you don't want a situation like this, because the chances are, if you have a situation like this for any of your designs, it's going to work sometimes, it's not going to work other times, right? Because again, it's like flipping a coin. Okay, but let's just move to the next thing that happens here. Okay, here, the active low asynchronous set occurs. All right, so what's going to happen once that asynchronous active low set goes to 0 set? It will set and the output will go to 1. Right? Because this is asynchronous, so it doesn't depend on the clock. Okay. All right. So any questions up to this point? The activity today is doing this. It's like 6 tiny diagrams. Actually, let's look at it real quick. If you look at the handout, there should be enough. There should be enough of the activity handouts on the tables, and the solutions are up here. So there's 6 of them. There's 3 on each side. Now, A, B, C. See to the right of each tiny diagram, I tell you whether it's falling edge trigger, rising edge trigger. I tell you whether it's synchronous or active low. Okay. Now, if you flip it on the other side, I got 3 more. D, E, and F. D, E, and F, I forgot to put the information you need, like the rising edge and all that. But if you go on Canvas, okay, go to Canvas and go to this meeting 11, it's shown there. Okay, so you'll have to go to Canvas to get what you need for the last 3. Okay. All right, so. Just a few more things here and then we'll be done for the lecture part. And let me turn the camera. Okay, so lab 5. And again, lab 5 is not due until the week after next, so you're gonna have plenty of time for it. Lab 5 is basically lab 4 with memory. Okay, so lab 4 you're working on now, and again, that's due Friday of next week. When you do lab 5, you're gonna take a lot of what you did for lab 4. Some of the things you did for lab 4, you're gonna delete, you won't need for lab 5. But a lot of what you did for lab 4, you're gonna need for lab 5. And then you're gonna add memory. Okay, you're gonna add a couple of D flip-flop modules, and you're gonna add a register module. We're gonna talk about what registers are after the midterm Tuesday of next week. And then also lab 5, we give you a module or we give you the code to use in a module. And the code is Dr. Mealy wrote the code, but it's for a time multiplexer. So with the time multiplexer, you'll be able to put information on all the displays instead of just the one. Okay. But anyway, what I wanted to show you at this point is how to model a flip-flop. Okay, because there's some new things that you're going to need to know in order to do this. Okay, now what's not new is like any module, you got to give it a name. I called it DFF. And you're going to have to declare inputs and outputs. So the flip-flop that we want you to model, it's going to have a D input, a clock input, just like all D flip-flops do. And it's also going to have an enable, it's going to have a reset, and it's going to have a set. Okay, so you're going to have to declare what is it? 5 inputs, and they're all single bit. Okay, this is, as you see in the diagrams, they're all single bit, and then you'll have to declare the 2 outputs. All right, so you should know how to do that by now. That's why I'm not going in any detail on that particular thing. But then after you have your inputs and outputs defined, you're going to use an if statement. Now, prior to this class, when you used an if statement, what did that if statement have to go within?
Always combination.
Right, and always home for combination, okay? Well, when you're dealing with a sequential circuit, like a flip-flop, and you're using an if statement, it also has to go within an always block, but it's not an always home, right? Because it's not combinational. It's always FF. Okay, so when you have something that's sequential, and you're going to use an if statement, or a case statement for that matter, but we're going to use an if here. It has to go within an always FF. And you write always FF, then you do that @ symbol. And then there's a sensitivity list. Okay, when I say sensitivity list, it's what's going to activate this. And the sensitivity list goes within parentheses, and you're going to put pause edge, and then COK. What do you think pause edge refers to? Rising edge. Yeah, because like we said earlier, another name for rising edge is positive edge. So you see, whatever you put within the parentheses here, that's when the block will be evaluated. So since we're making a flip-flop that's rising edge triggered, we want it to be evaluated on every rising edge of the clock. So that's why you see pause edge clock. Okay? And then you would put begin. Okay, then we're going to start our if statement. So if, and you want to make the highest priority reset, the second highest priority set, and then the third enable. So to do that, we start with reset. Now, I've noticed that most people, in fact, I think just about every one that I've actually seen writing the code for an if statement, that whatever the condition was, like say you had a condition that had to equal 1, like in the parentheses, you would put whatever the variable is and like 2 equal signs and a 1, okay, which is fine, that will work. But you can also just do this. You can just put right? Like if you want an active high reset, you can just put reset and it basically takes it as true. You know, like if true, meaning if active high, then we want Q be 0. Okay, now I'm going to explain this symbol here in just a second. Now, if you wanted an active low reset, instead of doing reset 2 equal signs equal to 0, you could just put an exclamation point right before the reset, and that would make it active low. Okay, the exclamation point inside the sensitivity list of an if statement is the same as like a tilde, like in a Boolean expression. Okay, but we want to make all our inputs for lab 5, we want to make them all synchronous and we want to make them all active high. Okay, so if resets high or 1, we're going to make Q equal to 0. Now notice I use this less than and then equal sign instead of just an equal sign. And you have to do that within an always FF block. Okay, within an always comb, you use the equal sign when you're assigning the output. But within an always FF, it's got to be the less than the equal sign. Okay, if you just put an equal sign, it's either going to give you an error or if it doesn't give you an error, it's not going to model the circuit the way it should. And that has to do with, that has to do with what's referred to as non-blocking and blocking. Okay, when you have the less than with the equal sign, that's called non-blocking. When you just have the equal sign, it's called blocking. Now, I don't know where these words come from. If anyone ever finds out, let me know. Like, I don't know why they call this blocking, why they call this non-blocking. I know the difference, but where the names come from, I'm not sure. See, when you have blocking, right? When you use the equal sign, which is what you do for a combinational, right? And again, the non-blocking is sequential, so that's when it's the always FF. Well, when you use the blocking, the equal signs, if you had code like this, where first you assign B to A, and then you assign C to B, well, this would make C equal to A, okay? Because when Verilog models this, it's basically going to take all 3 of these, A, B, and C, and just directly connect them together, like with a piece of wire. Okay, so if you do this, it makes it like a node, okay? But if you do this, the non-blocking, and you do the same thing, but instead of using the blocking, the equal signs, you use this less than equal for the non-blocking. Well, it doesn't do this. What it does is it puts memory in between. So, you know, here, C would not equal A. Okay, because you would have A, B, and C separated by essentially latches. Okay, so the reason I bring this up is because a common error, the most common one, is that people will use the equal sign within an always FF, and even though it's within the always FF, and I'm going to show you how you create a latch within an if statement. If you don't use the proper assignments symbol, it may not happen the way it should. Okay, and the reverse is true also, that if you're doing a combinational and you're not using the equal and you're using less than an equal, you could get a combinational circuit that has memory, that has additional circuitry. Okay, which again, in this class, it may still work. Okay, because we don't really have timing issues. But for your final project, depending on what you're doing, and especially for the microprocessor that you build in CPU233, you don't want additional circuitry that you don't need, because that's going to affect the timing. Your microprocessor would definitely not work if that's the case. Okay, but let's get back to this. So we would have if reset, make Q 0, else if. Okay, else if set. Okay, so this would make set second priority because it comes after reset. Q assigned to 1. Okay, if we're not resetting and we're not setting, that's when we're going to load or enable. Okay, so we would put else if enable. Now in lab 5, it might be called enter, but again, remember, enter, label, load, all the same, mean all the same here. So what are we gonna put? If we're not resetting, we're not setting, and we're loading, right, we're enabling, what do we want to set Q equal to on the positive edge of the clock? When you did a timing diagram, if we're not resetting and we're not setting, how do we get what Q is? D, right? You would set Q equal to D, or assign Q to D. Okay, so any questions here? See, the way you would change the priority is just change the order. Like if I wanted to make set the highest priority, I would first do if set and then else if reset. Okay, but we want to make reset the priority. So that's why we put it first. Okay, now what do you typically end an if statement with? I have if and else if, else if. So what would you typically do in a cone like we're doing previously? Else. Right, else. But here, because we want memory, we leave the else out. Okay, the way you create a latch, or one of the ways to create a latch in System Verilog is that with an always FF, you use an if statement and you don't end it with an else. Okay, so purposely here you would leave out an else. So, you know, come up here. Okay, and in System Verilog, the 2 backslashes mean a comment. So you see no else. And this creates a latch. Where next data Q is just going to equal Q. And then you would end this begin, then end mod. All right, so this is the code you need. Now, I left some things out. You know, I left out the declaring of the inputs and outputs, okay? But you should be able to do that. Also, thinking back to an always comb, when we did the if statement, what was the additional thing you had to do when you declared an output? If the output was within
the quote logic.
Right. Remember between output and the name of the output, you put logic, and you have to do that when you have an output that's within an always block, whether it's an always comb or an always FF. So when you declare Q, right? When you declare Q, you would have to put that logic like you did for the always comb for any outputs within an instance. Okay, but this is the code you'll need for the, or most of it anyway, for the D flip-flop module for lab 5. Okay. Let's see, is there anything else I wanted to mention? Do you have any questions about anything we covered?
Is it?
Oh, if we were to finish it? So are you saying over here? All right, well, let's see. Let's see what happened here. It's set here because of the active low asynchronous. And actually, well, where do you see it going low? Oh, right here. You're talking about, oh yeah, you're right. Yeah, I didn't see that at first because it would go high here, and then yeah, we have another rising edge, and at that time we're not setting, we're not resetting, so Q would depend on D at the time of the rising edge. So yeah, you're right, it would go to 0. And then it would just stay 0, right? Because, oh wait, over here what happens? Over here what happens?
High.
Yeah, it would go high at this point, right? Because the asynchronous set goes low again. So right here it would go high. Yeah, that's good. Yeah, I didn't see that at first, but you're right. It would go low at this point because, again, we're not resetting, we're not setting. So at this time of the rising edge, Q would just equal what D is. Yeah. Any other questions? I know the lecture, it was probably the longest lecture, but there was nothing today that you needed to know for lab 4 because you had all the information for lab 4 already. So after you do the activity today, you know, you should work on lab 4. You don't, I mean, if you have lab 4 done, you could do the module for the D flip-flop. Now, if you do that, on Tuesday after the midterm, I'll give you some additional information you'll need in order to simulate it. Because when you have a sequential circuit, there's something additional you have to put in your sim file in order to test a sequential circuit, but I'll give you that on Tuesday. All right, any other questions or concerns? All right, well, like I said, work on the activity. Once you're done with that, work on whatever lab you're on.